All right, today we're going to look at exponential growth and compound interest. Exponential growth, compound interest. The first three slides are going to be formulas. You might want to pause the video and write these down because that's what you're going to use all the way through. The first two, population growth is given by this formula right here. The P sub 0 is population at the beginning or at time 0. E is just a number. K is going to be our growth rate. Everything you see today is going to be, every time you see K, it's going to stand for growth rate. T stands for time all day long. So compounded interest compounded continuously. We've seen compound interest, but never continuously. If it says continuously, if you look at this is the exact same formula, but now the P stands for your principal that you start with. K is your interest rate, which is your growth rate, like it was last time, and T is still time. Okay, growth rate and doubling time. Stuff still means the same stuff. When you see T, it stands for time. K is your growth rate. Again, every time you see K, so if you're looking for your growth rate, you're going to do it this way. If you're looking for how long it takes to double, you do it that way. And when you multiply your growth rate times your time, it's always going to equal natural log 2. So natural log 2 is kind of a constant in that formula. Probably looking more at this one the most and this one, but all three of those are exactly the same formula, just written different ways. Models of limited growth. This kind of model is used, didn't mean to do that. This kind of model is used when a population levels out or something levels out. For example, if there's a flu epidemic, a lot of people start getting it, but eventually it levels off to a certain point. Not everybody in the whole world gets the flu at the same time. So even if it's an epidemic, it kind of levels off or limits itself. And I'm going to show you an example in a minute of a population that doesn't limit itself like that. So those are your formulas for the day. And if you got those down, I'm going to show you one example of each one, and you should be good to go after that. So here's the first one. It's a population. In 2011, the population of Mexico was about 113.7 million. That's a lot of people. And the exponential growth rate was this, 1.1% per year. So that's going to be our K. Estimate the population in 2015. Okay, so I'm going to say my formula P of T is 113.7 E, and my growth rate is 1.1%. You need to change it to a decimal, 0.0011, and T. Now, what I know is T, I'm looking for 2015, so that means T is going to be 4 because it's 4 years have passed since 2011. So all you do is take your calculator, punch that straight in, and I get 118.8, which is million people. And now the second one says, the second part says how long will it take to double. So because it's doubling now, I'm going to use the doubling formula. So I'm going to do a T equals natural log 2 over K. All right, so we already found K. K is 1.1%, so I'm doing natural log 2 divided by 0.0011. Again, change it to a decimal. You punch it in, and you get 63.0. So about 63 years before that population doubles. So there's two of the formulas into play already. All right, let's try another one. All right, suppose that $2,000 is invested at interest rate R. I mean, I should have put K right there because we're using K instead of R today. Compounded continuously and grows to 25.0465 in 5 years. What was the interest rate? So I'm using this one. I'm using P of T equals principal E to the KT power. I'm looking for K. So PT means what you ended up with. So it's 2504.65 equals 2,000. That's my initial principal. E, interest rate I don't know. Time I do know, 5 years. I'm doing 5K. All right, so what I'm going to do first is divide both sides by the 2,000. I'll punch that in real quick. 2504.65 divided by 2,000. That's how you move that 2,000 over. Did something wrong with my calculator. Give me just 1 second. 2504.65 divided by 2,000. Sorry about this. And I get 1.252 equals E to the 5K power. Now, here's the secret to doing this. Once you get there, you need to get the E gone. You need the K by itself. So what I'm going to do here is what we did yesterday. I'm going to do ln of both sides. When I do natural log on both sides, one side just becomes 5K. The other side you can punch straight into your calculator in a second. So I have 5K equals natural log 1.2523. So I'm going to divide both sides by 5 and punch it in. So I'm going natural log 1.2523 divided by 5. And I get 0.044, actually 0.045. So my interest rate is 4.5%. All right, then it says, what will the balance be after 10 years? So now I can just say, okay, what the balance be in 10 years, that's the final amount. So I'm going to do 2,000 now. Now I know the interest rate's 0.045 and the time is 10 years. So I'm going to put both of those as my exponent. So I can punch that straight in my calculator just the way it is, 2,000. Hit your E button, it pops up E, and I'm going 0.045 times 10. And my exponent, hit enter. And it's this much after 10 years, $3,136.62. You may want to punch it in your calculator. Make sure you're getting the exact same thing I did. And then again, it says how long will it take to double. So we're right back to the doubling thing again. Remember, T equaled, when you're doing the doubling function, T always equals natural log 2 over K. And we know what K is. K is our interest rate, which was 4.5%. So I'm just going to do natural log 2 divided by 0.045, and I get 15.4 years to double that money. There's also a secret thing called the rule of 72, which gives you an estimate. If you divide your interest rate into 72, it gives you how long it takes money to double as an estimate. Not exactly, but an estimate. All right, the population of Kenya is now doubling every 28.2 years. What is the exponential growth rate? Okay, so this is a doubling thing. Population is doubling, so I'm going to say, it wants to know what the growth rate is. So I'm going to say K equals natural log 2 over T, which is time. And it gave me the time in the problem. So the time is 28.2, so I'm going to, and that's years, by the way. So it wants to know what the growth rate was. So I'm just going to punch it in, natural log 2 divided by 28.2. And I get 0.0245, actually 0.0246. So my growth rate is 2.46%. What would be my growth rate there? How fast the population's doubling? Crazy. Pretty high. All right, this is going to be one of those where it's limited growth, where, let's just read it. A lake is stocked with 400 fish of a new variety. The size of the lake, the availability of food, and the number of fish restrict the growth of that type of fish in the lake to a limiting value of 2,500. So the population is going to grow, but never more than 2,500. The population is closer and closer to this time, T, in months, and is given by the logistic function that I wrote down right there. Find the value of the population after 10 and 15 months. We're going to see if it's reached the peak in 10 months or 15 months. So all I'm going to do to figure that out is I'm going to put a 10 and then a 15 where I see the T. I hope you can see it. It's right there after the negative 0.32. So I'm going to go 1 plus 5.25 e to the negative 0.3 t times 10. Now you got to be so careful when you punch this in your calculator. Your whole denominator needs to be in a parentheses, and if you do that, you should be good to roll right there. So I'm punching that in. Actually, I can punch, if I go to a better way to do it, just thought about this, is go to y equals, punch it in your y equals very carefully, then go to your table and set your table to increase by 5s, and you will see exactly what that is. You'll see both answers. So P of 10, when I punch all that in and go to my table, I'm seeing 2,059.3. Obviously there's not 0.3 fishes, but or fish. I don't know if you say fishes or not. So about 2,059 in 10 years. In 15 years, do the same thing. I'm just still looking at the table. So if I look at the table for 15, I'm seeing this many, 2396.3 fish. So still not quite to the max, or what this is saying, it limits it. And I'm looking at my table even more. In 20 years, it's 2478. So what's happening? The growth really slows down. The closer it gets to 2,500, the growth really slows down, because the lake just can't handle that many more fish. So, and the food supply cannot either. All right, so that's pretty good. That's a good example of all those formulas. Make sure you have those down in your paper. We'll work on those tomorrow. Do a few problems like that tomorrow when you come in. Exponential growth. See ya.